student at Cornell. I'm working with Jim Cordes and Shami Chatterjee, and I'm very excited to be talking to you today about exploring the ISM from Voyager to Pulsars. So I wanted to start out by giving the broad overview of my dissertation research, which is generally focused on radio wave propagation through plasma in a wide range of astrophysical environments, from the very nearby ISM that we can directly probe with Voyager to the diffuse ISM of our galaxy as probed by the dispersion and scattering of pulsar radio emission, to the local environments of pulsars, including their bow shocks and supernova remnants. And I'm even interested in studying plasma in the halo of our galaxy and in the extragalactic environments that we can probe using fast radio bursts. I'm also a member of the NanoGrav collaboration, which is hunting for nanohertz frequency gravitational waves using pulsar timing, and which relies on Green Bank for many of its observations. And NanoGrav relies heavily on a detailed understanding of plasma along the entire lines of sight to the pulsars in its array. So today, of course, I'm talking mostly about Voyager and complementary studies of the ISM with Voyager and pulsars. And there will be two main themes to my talk. The first theme is about how we can use in situ measurements of density fluctuations in the ISM with Voyager, but also with H-alpha emitting pulsar bow shocks to trace turbulence near the interfaces between stellar winds and the ISM, particularly near their stellar bow shocks. And the other main theme of my talk will be about how pulsar dispersion and scattering measurements can yield really complementary information about the density and structure of the sun's interstellar environment. And doing these kinds of complementary studies with pulsars is really critical to placing our understanding of the very local ISM from Voyager in a broader galactic context. So I'll start out by talking more about the work that we do with Voyager to study the ISM. So as many of you I'm sure already know, Voyager was launched back in the 1970s, and it sent two spacecraft on trajectories headed in roughly opposite directions, about 45 degrees above and below the ecliptic plane, through the nose of our heliosphere, which refers to the region of space around our sun that is dominated by the solar wind. And so Voyager was originally designed to take a tour of the outer planets, which it finished doing by the late 80s. And then in the early 90s, as Voyager continued to be operational, it transitioned into becoming an interstellar mission. And so Voyager I finally reached interstellar space in 2012 when it crossed the heliopause, which marks the boundary between our heliosphere and the very local ISM. And then Voyager I was followed 6 years later in 2018 when Voyager II crossed the heliopause as well. And so both spacecrafts are currently in the ISM and are our only spacecraft that can directly sample interstellar plasma. So Voyager has been one of our only direct sources of knowledge about the structure of our heliosphere and the nearby ISM. And so the sun expels the solar wind at supersonic speeds, as depicted in this very simplistic diagram on the right here. And the solar wind slows down at what's called the termination shock, which is where it compresses and heats as it slows to subsonic speeds, until the solar wind finally comes into pressure balance with the interstellar plasma flow at the heliopause, which is the boundary of our heliosphere. And then somewhere upstream of the heliopause is the sun's bow shock or bow wave, but the exact nature of this bow shock is really unclear at the moment. And this is predominantly because it is unclear whether the relative velocity of the interstellar plasma flow and the sun is actually above the fast magnetosonic speed. And so it's actually possible that instead of having a kind of classic sharp bow shock, we may in fact have a much more extended boundary layer that is often referred to as the bow wave. And then we also know from spectral line studies of nearby stars that outside of our heliosphere, the sun resides in this complex system of local interstellar clouds, which are depicted in this diagram on the left here. And our sun is actually moving towards the edge of one of these clouds as we speak. And so Voyager is currently in this region of space called the very local ISM, which is between the heliopause and the upstream bow shock or bow wave. And we call this the very local ISM because Voyager is still in close enough proximity to the heliosphere to actually see the occasional influence of solar activity on the interstellar plasma. So how do we actually study the plasma density using Voyager? Well, we use what's called the plasma wave system, or PWS. So Voyager has a number of different instruments on board, which are all depicted in this diagram on the right here. Now, not all of the instruments that were operating while Voyager was within the heliosphere touring the outer planets are operational today. So currently, we mainly have a couple of cosmic ray instruments, a magnetometer, and PWS, the plasma wave system. And PWS is one of our only tools for actually measuring the density of the plasma that Voyager is traveling through. And so the way that Voyager does this is it uses PWS to measure the voltage difference across these two radio antennae, which are located on either side of the magnetometer boom. And then we just use Fourier methods to convert the resulting voltage time series into frequency time dynamic spectra of the plasma's electric field. And so the methods that we use to analyze these voltage time series are very similar to the methods that we use in pulsar astronomy. And the typical time and frequency resolution and bandwidth of these resulting dynamic spectra are shown in this table here. So in this plot, I'm showing you all of the data that was recorded by Voyager 1's PWS since Voyager 1 crossed the heliopause in 2012 through early 2020. And so in this top panel, what you're looking at is the relative electric field intensity as a function of frequency versus time in years. And you can see an equivalent distance of the spacecraft from the sun on the top axis. And then in this bottom panel, we have a schematic that's pointing out many of the various relevant features that appear in this spectrum. But the main one that I want to point you to, which is the most obvious, are these bright bursts of power in the spectrum, which are called plasma oscillation events. So these are plasma oscillations that are triggered upstream of shock waves that originate within the heliosphere. And so when the sun emits something like a coronal mass ejection, this sends shock waves coursing out through the heliosphere and actually into the very local ISM. And upstream of these shock waves, we see these transient plasma oscillation events. So the lower frequency cutoff of these plasma oscillations is equivalent to the plasma frequency, which is directly related to the plasma density. And so by tracing the frequency of these plasma oscillation events, we can actually infer the plasma density along Voyager 1's trajectory. And so you can see the density on the right-hand axis here. So these plasma oscillation events have been really useful probes of the very local ISM, predominantly because they're one of the only tracers of the effects of solar activity on the interstellar plasma. And they've demonstrated that the heliopause is not a sharp, hard boundary, but it is in fact porous. But one of the main issues with relying on these plasma oscillation events for measuring the density is that they are inherently unpredictable. So you can see that about one plasma oscillation event has been detected per year since Voyager 1 crossed the heliopause. But in all of these cases, these plasma oscillation events tend to be short, in the longest case up to a year, but that was highly unusual. And as such, Voyager 1 was essentially relying on fortuitous, unreliable detections of these plasma oscillation events in order to measure the plasma density. And so when I joined the Voyager team last year as a guest investigator, one of my first goals was to try to extract as much density information out of this PWS spectrum as possible, in particular by searching for plasma oscillations that had not been detected previously. And so what we discovered was actually rather surprising. We learned that Voyager 1 has been detecting not only transient plasma oscillation events, but also a persistent plasma wave signal. So in this top panel on the right, I'm showing you the same PWS spectrum, but now we're looking at data from 2015 through early 2020. And so you can see several of the plasma oscillation events that were detected before. And now in this middle panel, I'm showing you the same spectrum, but with a different color stretch. So now we're looking at the intensity of the data right above the noise threshold. And so all of these plasma oscillation events appear saturated out because they're so bright. But you can see this very faint narrow band signal begin to appear around early 2017 and last through early 2020, which is the latest date shown on this plot. And in this bottom panel, you can really see this very faint persistent signal pop out. Here we've smoothed the spectrum in time using a boxcar filter. And so you can really see that this very narrow band signal in the plasma wave spectrum is persisting for at least 3 years of the Voyager I data. So this discovery was very surprising because this persistent plasma wave signal was entirely unlike the plasma oscillation events that had been detected previously. By every mark, it's very narrow band, is extremely weak, and it is present even in the absence of these solar activity triggered plasma oscillation events. And so its physical origin appears to be distinct from these plasma oscillation events. So it is independent of solar activity. And moreover, the fact that this signal persisted for over 3 years in the Voyager I data indicated that we could use it to obtain a nearly continuous sampling of the plasma density along Voyager I's trajectory. So this really transformed our ability to study the distribution of the plasma density along Voyager I's trajectory. Now, I said nearly continuously because you'll notice that there are these very big vertical stripes in the spectrum, particularly in 2019. And these are periods where the spacecraft telemetry was severely degraded, and in part due to not having enough DSN antennas available. And so during these periods of degraded telemetry, we are unfortunately unable to resolve this very faint, persistent plasma wave signal. But regardless, this detection was very, very exciting. And it was featured on in the August issue of Nature Astronomy, and it also prompted a rather amusing progression of news coverage. At first, it was discussed as a persistent hum, and we called it a hum because the peak frequency of this plasma line is around 3 kilohertz, which is in the audible frequency range. But then the persistent hum became an eerie hum, and the eerie hum became an ominous hum, which was rather concerning. But regardless, this discovery left open a number of open questions, the main one being, what is the physical origin of this persistent plasma wave signal in the Voyager I data? And the most promising explanation thus far is that this persistent plasma wave signal is quasi-thermal noise, or QTN. So QTN is very analogous to Johnson noise. It refers to the voltage spectrum that you get from electrostatic fluctuations in the plasma surrounding the Voyager antenna. And so QTN has been detected on a number of spacecraft, including Ulysses and Galileo, all of which were within the heliosphere. And the properties of the QTN spectrum really depend heavily on the plasma parameters, particularly its density and temperature. And typically, to detect quasi-thermal noise, you need an antenna that is longer or much longer than the Debye length of the plasma. Now, Voyager I has an antenna length of about 7 meters, whereas the Debye length in the very local ISM is estimated to be around 30 meters. And so for typical assumptions of the plasma parameters, it would normally appear that Voyager I should be unable to detect quasi-thermal noise. So in this plot on the right, we have the quasi-thermal noise spectrum that is expected for typical assumptions for the plasma parameters in the very local ISM and the size of the Voyager I antenna. And so what would be expected is an extremely small peak at the plasma frequency. And so normally for an optimally designed antenna, the quasi-thermal noise spectrum would show a very large peak at the plasma frequency, which you could then use to infer the plasma density. But in the case of Voyager I, under these typical assumptions, we really would not expect to be able to detect any peak in the plasma frequency in the QTN spectrum, particularly because the Voyager I preamplifier noise level is also orders of magnitude larger than the predicted levels of the QTN spectrum. But this picture changes when you change your assumption of a Maxwellian electron velocity distribution. And so in essence, if you actually add a significant suprathermal tail to the electron velocity distribution, you can actually get a very large peak at the plasma frequency in the QTN spectrum, which would just be detectable above the Voyager I preamplifier noise. And so if we are indeed detecting QTN with Voyager I, then this implies that there is a significant population of suprathermal electrons in the very local ISM plasma. So this is ongoing work that is really interesting and has been predominantly led by Don Gurnett, who is the PI of the PWS instrument on Voyager. And so for more on the kind of plasma physics implications of this discovery, I would point you to this paper, which should be coming out shortly in AppJ. Now, we have continued to detect this persistent plasma line from Voyager I. In fact, it has continued to be a critical source of density information far from the heliopause. And so here I'm showing you the most recent data from Voyager I that is extending up through 2021, August of this year. And I've pointed out where this persistent plasma line has persisted in the more recent data. And so it looks very faint, in part due to the time resolution in the spectrum, which has gotten worse. But we are continuously trying to improve our signal processing techniques for extracting this extremely weak signal. And so the detection of this persistent plasma line has also yielded another really interesting discovery, which has been this pressure front in the very local ISM, which Voyager I traversed in mid-2020. And so you can see this pressure front here as this jump in the plasma density from about 0.11 to about 0.15 per cubic centimeter. And this pressure front was also observed in the magnetic field data from Voyager I. Voyager I also saw a jump in the magnetic field strength, which was entirely consistent with the magnitude of this density jump. And so this implies that Voyager I crossed some sort of pressure front in the very local ISM. Now, one could ask whether this pressure front is just a shock wave coming from within the heliosphere, similar to the shock waves that we've seen in earlier data from Voyager I. But we haven't actually seen any plasma oscillation event activity that normally precedes a solar origin shock wave. And so in the case of this pressure front, it appears likely that Voyager I has actually crossed over a nascent structure in the very local ISM, as opposed to seeing another shock wave from within the heliosphere. So this has been a really interesting detection, and for more on the discovery of this pressure front and its implications, there is a paper that came out earlier this year in AppJ, which was led by Len Berlaga, who was the PI of the MAG instrument. Now I'd like to transition into talking about how we actually use this density information from Voyager I, in my case, in order to study the properties of turbulence. And so one of the main ways that we characterize density fluctuations in the ISM is using the turbulence wave number spectrum, which is given by this equation here. And so the power spectrum of density fluctuations depends on wave number Q, which is inversely proportional to the length scale of the density fluctuations. And the spectrum has an amplitude Cn squared and a spectral index beta, which is 11/3 for Kolmogorov turbulence. And so this spectrum extends from the outer scale QO, where turbulence is driven, to the inner scale QI, where it dissipates. And so Voyager is capable of constraining density fluctuations in this wave number spectrum over a fairly broad range of spatial scales, from tens of kilometers up to tens of AU. And on the plot on the right here, I'm showing you are constraints on the density fluctuation power spectrum versus wave number using not only Voyager, but also other kinds of pulsar observations. And so pulsar observations are really useful for comparison because they can probe larger spatial scales in the ISM than Voyager is capable of doing. So here I've circled the specific constraints on the spectrum that we get from Voyager. So Voyager constrains the largest wave number region as shown by these green points. And then in the mid wave number regime, we get constraints shown by the blue, orange, and green points. And so one of the main results that we find is that the amplitude of this turbulence wave number spectrum detected by Voyager is about 2 orders of magnitude larger than values of Cn squared, the spectral amplitude, in the diffuse warm ionized medium. So previous studies of turbulence in the ISM have generally shown that the amplitude of turbulence in the warm ionized medium is around 10 to the minus 3.5. But in the very local ISM probed by Voyager, we see that this spectral amplitude is around 10 to the minus 1.6. And so one of the main explanations for this amplified turbulence is that Voyager 1 is seeing a superposition of both interstellar and solar wind turbulence, which is a product of its location in close proximity to the heliosphere. Now, we also see a very large excess of power in this spectrum, particularly at the largest wave numbers probed by Voyager. And so these large wave numbers correspond to the smallest spatial scales that Voyager is capable of probing. And this spectral excess has also been observed in previous studies of density fluctuations detected by Voyager 1. And it has been argued that the spectral excess arises from kinetic scale processes that are mediating turbulence at these scales. These are scales approaching the proton gyro radius and the inner scale of the wave number spectrum. But it is really unclear whether the spectral excess could have any kind of bias from the techniques that we're using to extract density fluctuations at these very small spatial scales. These are measurements that are really pushing up against the limited time and frequency resolution of the PWS spectrum. So the exact origin of the spectral excess at these large wave numbers is still unclear, but it is highly interesting. And also it is very important to note that Voyager is currently uniquely capable of sampling this high wave number regime in the ISM. And so it is really critical that we continue to try to understand the behavior of the wave number spectrum at these large wave numbers probed by Voyager. Now, I'm going to transition now into talking about how our results from Voyager compare to the turbulent density fluctuations that we see around pulsar bow shocks. But before I do that, I wanted to briefly pause and see if there are any questions thus far.
I'll ask one. I had to step out for a little bit, so I'm sorry if you may have already addressed this, but are there instruments like this on any other probes like New Horizons that are on their way out of the solar system that would give you better frequency resolution, wider bandwidth, better time resolution? That I'm guessing it would be many years down the road, but that might eventually be able to help you improve on what Voyager's giving you.
Yeah, that's a great question. So there are instruments like this on other spacecraft. New Horizons and IBEX are currently the only other spacecrafts that are really sampling the kind of outer heliosphere and kind of remotely inferring the properties of the very local ISM. But unfortunately, neither of those spacecraft will still be operational by the time that they leave the heliosphere. And so currently Voyager is really our only option for doing this kind of science. But at the end of my talk, I will briefly discuss a new mission concept called Interstellar Probe that is being developed and which would essentially be Voyager's successor in doing this kind of science.
Great, thanks.
Okay, if there are no other questions, then I will move on. So now I'll be talking about density fluctuations around pulsar bow shocks, and this may seem like kind of a strange transition, but in fact, H-alpha observations of stellar bow shocks are one of our only other in situ probes of density fluctuations in the ISM. And the reason for this is that the morphology of stellar bow shocks is directly related to the density of gas in the ISM that the star is traveling through. And so I'll mainly be talking about pulsar bow shocks, but this analysis could easily be extended to H-alpha emitting bow shocks that are observed around many other stars at a variety of different life stages. And I also want to emphasize that both Voyager and H-alpha emitting bow shocks allow us to probe density fluctuations in a rather unique environment, which is near the interface of stellar winds and the ISM. So pulsar bow shocks are capable of probing density fluctuations around spatial scales of thousands of AU up to a fraction of a parsec. And so here on the right, I've circled our constraints on the wave number spectrum that we get from these bow shock observations. And one of the main bow shocks that we use to do this is called the Guitar Nebula. So the Guitar Nebula is the bow shock produced by pulsar B2224 plus 65. This image on the right here is showing the entire nebula in H-alpha as imaged by Palomar. And here on the bottom, I'm showing you 3 images of the bow shock nose as indicated by this white square. And so these images on the bottom were taken by Hubble in 1994, 2001, and 2006. And so you can see that over the course of these 3 observations, the morphology of the bow shock has changed. And this pulsar has a very large transverse velocity of about 770 kilometers per second, which means that over the course of these observations, the pulsar has plowed through hundreds to thousands of AU in the ISM. And so the way that we resolve density fluctuations from these H-alpha images is by fitting for the bow shock standoff radius. So in the thin shell limit, the bow shock standoff radius really depends on only a few factors given by this equation here. It depends on the spin down luminosity of the pulsar E dot, c the speed of light, rho the interstellar density, and v star the velocity of the pulsar. And so you can see that by resolving changes in the standoff radius over time, we can actually infer density fluctuations in the ISM around the pulsar. But of course, this has the important assumption that the spin down luminosity and the pulsar's velocity are constant. And when it comes to the pulsar's velocity, this is a fine assumption over the time scales that we're considering, but if you're at all familiar with pulsars, then you could probably think of one very obvious exception to this constant spin down luminosity assumption. And that is, of course, pulsar glitches. So glitches are when the pulsar's spin period and period derivative change in an almost instantaneous fashion. And one of the easiest ways to think about the effects of a glitch is just to look at the simplest expression for the rotational kinetic energy of a spinning neutron star. So that's given by this equation here. And this rotational kinetic energy depends on the moment of inertia I and the spin period of the pulsar P. And so in the case where you have a normal, happily spinning down pulsar that isn't experiencing any glitches, what you have is some amount of spin down, which results in a period derivative P dot. And this gives you a change in the spin down energy, E dot, which we often also refer to as the spin down luminosity. And assuming that all of this spin down energy gets converted into the relativistic pulsar wind, this is one of the key factors in determining the pulsar's bow shock standoff radius or not. Now, when you have a glitch, you have a change in the spin period, and you can also have a change in the spin period derivative. And so ostensibly what you have is a change in the spin energy and spin down energy of the pulsar. And presumably some of this energy, which is released during a glitch, could affect the standoff radius. But there's a huge caveat to that, which is that we really don't know how much of this energy released during a glitch would actually make it into the pulsar wind and out to the bow shock. And so it is quite possible that the energy released from glitches may impact pulsar bow shocks, at least for very large glitches, and possibly for kind of exotic nulling pulsars where you see periodic changes in the spin period and period derivative. But in the case of the Guitar Nebula, we really don't see any evidence that glitches are driving the bow shock morphology. So in this image on the right, I'm showing you a close-up of the bow shock nose. And this axis is showing you the direction of the pulsar's proper motion. And so these 4 red circles are indicating the location of the pulsar during a recorded glitch. And so none of these glitches appear to have been large enough to cause any observable change in the pulsar's bow shock morphology. And so it appears very unlikely that glitches are impacting the bow shock standoff radius, at least in the case of this pulsar and this bow shock. But I do want to emphasize that it is very possible that glitches are relevant for the bow shocks of other pulsars, and that this is an effect that hasn't really been explored yet. But why have I really been harping on about, the effects of glitches and why it doesn't matter? Well, the main reason is that I really want to convince you that when we resolve changes in the standoff radius of the bow shock over time, we really are probing density fluctuations in the surrounding interstellar gas. And so here I'm again showing you our constraints on the density fluctuation power spectrum using the Guitar Nebula. We also looked at the H alpha bow shocks of 4 other pulsars, which are indicated by these colored triangles. And in all of these cases, we again see values of the turbulence spectral amplitude Cn squared that is very large compared to values of Cn squared that are considered typical for the diffuse swarm ionized medium. And so at this point, it's really unclear whether these large spectral amplitudes are actually produced by interactions between these bow shocks and the surrounding ISM, or whether we are potentially just seeing a selection effect because we are only looking at H alpha emitting bow shocks. And so the reason I say that is because in order to detect H alpha emission from these bow shocks, you need a large enough density of partially ionized gas around the pulsar. And so this potentially means that H alpha emitting bow shocks bias us towards regions of larger, more amplified density fluctuations. And so at this point, it's really unclear whether this large spectral amplitude we see from turbulence around pulsar bow shocks is actually representative of pulsar bow shocks generally, or whether this is a selection effect. But I do want to emphasize that actually these large spectral amplitudes, which we see not only around pulsar bow shocks, but also in the very local ISM probed by Voyager, these large spectral amplitudes are not really unique when you consider the large scale variability of turbulence throughout the ISM. And so one of the ways that we can characterize turbulence across the diffuse ISM is using other remote observations of pulsars, particularly pulsar dispersion and scattering. And so here I'm showing you constraints that we get on the turbulence wave number spectrum from pulsar dispersion measure variations, which indicate orders of magnitude variability in Cn squared between different pulsars' lines of sight. So DM variations are extremely useful probes of the ISM. I'll briefly remind you that the pulsar DM is just the integrated electron column density along the pulsar line of sight. And DM variations in time are routinely observed by pulsar timing arrays like NanoGrav. And so on the right here, I'm showing you a few different DM variation time series that were observed by NanoGrav over a 12.5-year long period. And in this top panel in orange, you can see an example of DM variations that are predominantly related to turbulent density fluctuations in the ISM along the line of sight to the pulsar. And then in blue, you can see an example of DM variations that have a periodic component that is actually related to the pulsar's line of sight periodically crossing through the solar wind as the Earth orbits around the sun. And in this bottom panel, I'm showing you a slightly different, more unusual example of pulsar DM variations. So in this bottom panel, we see for this particular pulsar J1713, these two very strong dips in the DM over a several year-long period. And while the exact origin of these strong dips in the DM time series are unclear, it appears possible that these dips in DM are essentially produced by lensing through discrete plasma structures. And so DM variations are useful for tracing a broad range of phenomena in the ISM, not only turbulent density fluctuations, which we can use to constrain the turbulence wave number spectrum, as I was just showing you, but DM variations can also be used to trace potentially discrete AU scale plasma structures in the ISM, and they can also be used to trace effects within our heliosphere, such as solar wind variations and coronal mass ejections. And the effects of the very local ISM have actually yet to be fully explored when it comes to DM variations. Now, pulsar DMs are also really useful for comparing with Voyager data and studying the sun's interstellar environment, particularly by looking at the spatial distribution of pulsar DMs. So when you have both a DM and an independent distance or parallax measurement for a pulsar, what you can get is the mean electron density along that pulsar's line of sight. And so by looking at the DMs of nearby pulsars with independent distance measurements, we can actually get independent estimates of the mean electron density along many different lines of sight and compare those to spectral line studies of nearby stars. So in this spoke diagram on the left, I'm showing you the mean electron densities along various pulsar lines of sight within 500 parsecs of the sun. And these dashed lines indicate the 200 and 400 parsec distance marks. And so these three lines of sight highlighted in red are the three pulsars within 200 parsecs of the sun. And so you can start to see by careful examination of this plot that there are some patterns that can emerge in the average electron density along the lines of sight to these nearby pulsars, which directly traces the underlying structure of the density distribution. And this is really useful for comparing with our understanding of the local interstellar cloud complex from spectral line studies of nearby stars. So on the right here, I'm again showing you a diagram of the local interstellar clouds. The distribution of these has been inferred from spectroscopic observations of the closest stars. And these only trace about 5 parsecs around the sun. And so by looking at the larger scale distribution of pulsar DMs, we can place our understanding of this local interstellar cloud complex in a broader structural context. And in particular, there's been some recent work on the structure of the local bubble, which has indicated that pulsar DMs can provide a really important independent estimate of density. In particular, the local bubble refers to this supernova cavity surrounding the sun that's around 200 parsecs-ish wide. And it was originally believed that the local bubble was filled with million-degree, very low density gas. But a recent study that's been led by Jeff Linsky and Seth Redfield has actually shown that when you use the mean density implied by nearby pulsar DMs, you actually find that the density of the local bubble is larger than previously thought, and that the temperature of the local bubble is lower than previously thought. And so what they actually show is that when you use these pulsar DMs, you can estimate the size of the Stromgren sphere for the star Epsilon CMA. And what you find is that the size of that Stromgren sphere is actually consistent with the size of the local bubble. And so the implication is that the local bubble may in fact be the Stromgren sphere of Epsilon CMA. So this is potentially a really significant rewriting of our understanding of the local bubble. and is a very interesting example of how valuable it can be to combine these different remote probes of the ISM. And also how important it is to use these remote probes of the ISM to place our understanding of the nearby ISM probe by Voyager in a larger context. So at the beginning of this talk, I kind of implied that I wouldn't really be talking about NanoGrav, but I wasn't entirely truthful, because the reality is that all of the things I've talked about today are very relevant to NanoGrav, in particular to constructing a pulsar timing noise budget. So radio pulses from pulsars traverse many different kinds of structures in the ISM, all the way from the pulsar's local environment through the heliosphere and the solar wind before arriving at our observatories. And along their journey, the radio pulses experience a number of different propagation effects, which are broadly delineated in this diagram between different diffractive and refractive effects. And in particular, pulsars can experience various scattering effects like pulse broadening and scintillation, and extreme scattering events, but also DM variations in time. And all of these different propagation effects yield delays in the expected pulse time of arrival. And so this is really critical to understand for NanoGrav, because NanoGrav wants to detect the timing delays from gravitational waves. And so in order to detect the timing delays from gravitational waves, you must first disentangle chromatic timing delays that arise from propagation through plasma. And so this is a rather difficult task, because all of these different propagation effects are dependent on the observing frequency, which is partially to our advantage because gravitational waves are not dependent on the observing frequency. But the frequency dependence of these different propagation effects depends on the properties of turbulence and discrete structures in the ISM, which vary between different lines of sight, which is also very obvious when you consider all of the effects that I've been talking about earlier. So I wanted to give one brief example of one of these propagation effects that we still do not fully understand. These are scintillation arcs. So scintillation refers to the modulations of the radio intensity from a pulsar as a function of frequency versus time. Here on the top, you can see an example of a dynamic spectrum for pulsar B1133+16. And so you can see the intensity variations in the dynamic spectrum characterized by these kind of islands, which we call scintils. And when you take the two-dimensional Fourier transform of this dynamic spectrum, you get what's called the secondary spectrum, which is shown on the bottom here. And somewhat amazingly, what you see in the secondary spectrum for many pulsars are these parabolic arcs. And so these parabolic arcs appear to be ubiquitous among many pulsars. And in fact, much of our understanding of the ubiquitous of these scintillation arcs has actually been done using surveys carried out at Green Bank. And the curvature of these so-called scintillation arcs is directly related to the distance to the scattering screen that is responsible for this scintillation. But the exact origins of these scattering screens is really unclear. We don't know exactly what kinds of plasma structures in the ISM are responsible for scintillation arcs. And so one possibility that appears quite promising and which we are openly exploring is whether bow shocks could actually be responsible for scintillation arcs. So we actually have at least one example of a pulsar where we have a scintillation arc whose curvature is consistent with the scintillation arising from the pulsar's own bow shock. And so we're currently exploring whether this effect of scintillation from bow shocks may actually be one of the main origins of scintillation arcs. So I want to briefly summarize, and I'll come to the end of my talk, and I want to remind you of the kind of two main themes that I've been talking about, which are both related to probing the ISM as a dynamic environment by combining in situ and remote probes. And so the first main theme that I talked about was studying in situ density fluctuations with both Voyager and H-alpha emitting pulsar bow shocks. And what we found was that the density fluctuations near both the sun's bow shock and these pulsar bow shocks are significantly enhanced relative to density fluctuations in the warm ionized medium. But I also talked about how it's really critical that we continue sampling turbulence in this very high wave number regime, which is currently really only directly available through Voyager. And then I also talked about how critical it is to compare our understanding of the very local ISM to our remote probes of the ISM, particularly from pulsar dispersion and scattering. And one of the interesting outcomes of this, which is still ongoing work, is whether the local bubble may in fact be different in origin and structure than previously thought. So looking ahead, there is still a lot of work to be done. In particular, we still need to compare the magnetic field fluctuations that are observed by Voyager with magnetic field fluctuations that are probed by Faraday rotation from pulsars. And so one of the advantages of looking at magnetic field fluctuations is that they are arguably a more direct tracer of the underlying turbulence in the ISM. It's also still unclear exactly how turbulence gets transmitted through bow shocks and what the origin of these enhanced density fluctuations near stellar bow shocks actually is. And then we're also really interested in better understanding what the propagation effects of bow shocks are, particularly with regards to pulsar scintillation. But something else that I didn't really talk about was that there's actually really promising work that shows that we can use scintillation arcs of nearby pulsars to actually examine the structure of the local interstellar cloud complex. And all of this actually kind of relates to this broad overarching question, which is often posed in meetings about Voyager and probing the very local ISM. And it's this question of whether Voyager will ever reach the so-called quiescent ISM. And so when people refer to the quiescent ISM in this context, what they're generally referring to is the ISM beyond the sun's bow shock. But Voyager will not be operational by the time it reaches that distance. And furthermore, it's really unclear whether such a thing as the quiescent ISM really exists. We know from all of these complementary studies of remote sensing observations that the ISM is really complex, and it is full of supersonically moving stars that are producing bow shocks and many different kinds of complicated structures. And then I also wanted to briefly highlight this new mission concept called Interstellar Probe, which is currently being developed at Johns Hopkins Applied Physics Laboratory. And Interstellar Probe would essentially be Voyager's successor. And it is targeted for launch in the mid-2030s, and it would travel about twice as fast as Voyager 1. So over the same timescale of the Voyager mission, around 50 years, it would reach 350 AU, which is extraordinarily far. And so this mission concept, is still in kind of development stages, but if it happens, and I very much hope it does, then it will provide an extremely exciting opportunity to directly sample the ISM with much higher precision and accuracy than we can currently do with Voyager. So with that, I will happily take any more questions.
All right. Fantastic talk, Stella. Thank you very much. And also, it's really wonderful to see just what can still be done with, honestly, what's such an old instrument and is literally the most distant man-made object from Earth. So it's fantastic research. Before I turn it over to the audience, I did want to ask you one quick question or clarification for those of us who are not, pulsar people. What exactly is a glitch when it comes to a pulse?
Yeah.
How does that happen?
Normally when you think about pulsars, you can think about them kind of from the lighthouse picture where you see the radio mission periodically crossing your line of sight. And so we expect that radio mission to have a very specific, period. and also period derivative, because the pulsar is slowing down as it's losing energy, rotational energy. And so when a glitch happens, what you see is that the period of the pulses actually changes. And so it's no longer what you expect. And that change happens over a fairly short time scale. Normally, our constraint on that time scale is really limited by our observations, but it could be, anywhere perhaps from days to a month. So you see this really sharp change in the period of the pulses from the pulsar. And you also see this really sharp change in the rate of that period's change. So you see a change in the period derivative. And the origin of the glitch is still kind of up for debate. There are, different kinds of models for explaining how glitches happen. But the main model that most people work off of now is that it arises from essentially like vortex unpinning. It's related to the properties of the superfluid inside the neutron star. And so the physical origins are really complex and really related to the interior physics of the neutron star's structure. But that's the broad overview.
Okay, so definitely a rabbit hole.
Yes.
All right, thank you. All right, let's turn it over to Ryan.
Yeah, thank you for a nice talk. I have a few questions, but maybe I'll just ask one or two, and then we'll see if there's time for others. So can you go back to the image you have with the guitar nebula with the glitches marked?
Yes. There we go.
Yeah, so that one near 1975 looks kind of close to where it's kind of wide there. Maybe it's actually a little bit after it starts, but I was just curious, like, how do you know that that isn't somehow related to that glitch?
Yeah, that's a great question. So the answer is that one of the main things that we can do is we can use the observed change in the spin frequency and frequency derivative from this glitch to estimate the energy release during the glitch. And then we can convert that energy release into a change in the standoff radius. And what we find is that it's really unclear whether the glitch was large enough to actually produce a change in the standoff radius that's detectable on these spatial scales. So that's kind of the short answer, but the even shorter answer is that it's really hard to tell, especially because when the pulsar was back here, the bow shock was really back here as well. And there are all kinds of other effects that can influence how the bow shock is expanding into the surrounding medium downstream as the pulsar is moving further upstream. So that's kind of all the different flavors that are relevant.
Okay, and if I can just maybe ask one more. So we are pursuing building a real-time cyclic spectroscopy capability for the GBT, and for those who haven't heard the term, basically would allow us to get higher frequency resolution dynamic spectra for a large number of pulsars. So I'm just curious if you could speculate a little. So we thought a lot about that in terms of improving the noise budget for NanoGrav. I'm wondering if you can speculate on some ways that that will be useful for probing the ISM aside from just trying to correct pulsar times of arrival.
Yeah, so from what I understand, cyclic spectroscopy will really give us much better resolution in the secondary spectrum as well. So I think it will be really useful for studying scintillation and scintillation arcs. But I think as you said, that's the dynamic spectrum is one of the main targets of interest, particularly for studying intensity modulations that arise from density fluctuations in the ISM.
Thank you.
All right, let's turn it over to Jay.
Yeah, thank you. Great talk, really interesting. And we can stick right on this same slide because that's the one that's of interest to me. And I have two questions about this pulsar. with the 700 kilometer a second or 770 kilometers a second peculiar motion, how is this oriented in galactic coordinates?
Galactic coordinates. Oh gosh.
Okay, well, that's, I mean, that can be determined.
Okay, sorry.
I mean, that's in principle escape velocity from the Milky Way, so it's going.
Yeah. So, and that is, in essence, yes. And in fact, we do see at least one pulsar that I know of. I'm forgetting, let's see, I think it's something like J1740 plus 1,000 or something like that. That's actually fairly high above the galactic plane with a fairly large transverse velocity. And that's one of the pulsars where we actually see it kind of more like further along its escape route, which is really interesting. But yeah, these pulsars have insanely fast speeds. It's really remarkable. And something that I kind of like to think about is the fact that we realistically have thousands of these extremely fast moving pulsars distributed across the galaxy. So potentially we have thousands of bow shocks as well, potentially even more, being produced by these supersonic pulsars, which is kind of fun to think about.
And
Yeah,
we do also have a comment in the chat by Jim Cord saying that this pulsar is moving fairly parallel to the galactic plane. So
Okay.
it is unlikely to be shot out of the Milky Way anytime soon.
Okay, thanks, Jim.
And my other question is, which was not clear to me, was how you derive a turbulent power spectrum from this image, basically.
Yeah. So the main way is that we basically fit for the, let's see if I can, okay, here we go. We fit for this bow shock standoff radius. That's the first step. And so we can fit for the bow shock standoff radius directly by tracing the limb brightened edge of the bow shock. And then we can convert variations in the standoff radius over time into density fluctuations over time. And these density fluctuations over time are equivalent to density fluctuations over a given spatial scale, which is set by the pulsar's transverse velocity. So with basically we have a spatial offset then between the density in each of these epochs, and that spatial offset then corresponds to a wave number in the wave number spectrum. And the density fluctuations essentially give us the power spectrum. What we're getting for the wave number spectrum is the power spectrum of those density fluctuations.
I mean, is the basic idea that something that's more turbulent is fluffier and more difficult to shock?
So yeah, so the basic idea is that you see larger amplitude density fluctuations, basically. Yeah.
Okay. All right, thank you.
Yeah.
All right, well, since we are at the hour, we should conclude here, but I wanted to give one final thank you, Stella, for joining us today and talking about your work. And thank you, everybody, for joining us.
Yeah. Thank you.